This talk is about lattice-based group key exchange protocol in the standard model. I am Parhat Abla from Institute of Information Engineering, Chinese Academy of Science, and School of Cybersecurity and UCAS. In this talk, I want to talk about the backgrounds on lattice, ring learning with errors, and group key exchange. After that, I will mention the multi-party key reconciliation. And then I will talk weak group key exchange definitions and my instantiation. And then I will, finally, I will give my construction of group key exchange in the standard model. A lattice is in the Euclidean space Rn, is a additive group generated by the vectors. We say V1 to Vn. And a lattice is a discrete subgroup of Rn. We call V1 to Vn is the lattice basis of the lattice IL. Every lattice has many bases. Like in the picture, the red points are lattice points, and the V1 and V2 are these vectors. V1 and V2 is a basis of the vector, basis of the lattice, and the blue vectors, V1 prime and V2 prime, are also a basis of the lattice. In cryptography, we want a hard problem. We say a hard problem. That means cannot be solved in the classic computer very efficiently. We say efficiently. That means maybe 100 years. It takes 100 years or a very long time. On lattice, there's many hard problems like shortest vector problems and closest vectors problems and others. Here we just mentioned one of them. The shortest independent vectors problem, SIVP. The SIVP is, this problem is given a lattice L. Given a lattice means given a basis, like the red vectors, and it asks to find a shortest basis, like the red basis. This is very easy in the two-dimensional, but for 100 dimension going up hundreds or thousands, it's very hard. For a ring R, which is Zx quotient by x to the n plus 1, when the n is the power of 2, the ideals in the R correspond to a lattice, and we call these ideals ideal lattices. This ideal lattice, we have hard problems now, and if you want to construct a cryptographic scheme or system and base his security on the hard problem, but the lattice problem is not straightly based a cryptographic scheme. So 2005, Regu introduced the learning with errors problem. But the cryptographic schemes based on the learning with errors problems are very complex, and the public parameters are really large. So in 2010, the learning with errors problem, ring version of learning with errors problems are introduced by Lubashevsky, Packard, and Regu. This problem is like this, given the ring element AI, and another BI is computed by AI times secret S plus a EI. This EI is we say the EI is an error. And the goal of this problem is to find the S, given the A and the red B as much as one wants. And the goal is to find the secret S. If there is no the secret, the error E, it's very straight to find the S, because if given the B, we just inverse the A and multiply BI, and we get the S. But adding this error E makes this problem very hard. The decision version is very similar. This is given the A and the B, and it asks to decide whether this B is from it's from the ring LW sample, like computed like this, or it's a uniform sample. That means PI is just uniformly sampled from the ring R. It's known that the decision version of ring LW is as hard as search version. That means if we can base a cryptographic scheme on the decision version of ring LW, and this problem also based on the search version of ring LW, and it's also a reduction here that if one can solve the search version of this problem, so there is an efficient algorithm which can solve the worst case of SIOP problem on lattice problem on either lattices. The worst case SIOP problem on either lattices. So if a crypto system based on the decision ring LW problem, that means that this problem, if one can solve or break the crypto system, that also breaks the worst case SIOP problem on either lattice. It's known that most of the people believe that the worst case SIOP problem is quantum resistant. That means there is no efficient quantum algorithm that solves this problem. So we say that the crypto system is post-quantum. A group key exchange protocol is like this, given the n people. Here we just say 4 people here. And by transmitting the data through the public channel, this public channel is seen by everybody. We mean good people or bad people will see the public channel. And after all, they agree on the session key. We say K. After they have the K, and they encrypt the message and transmit to other. Here's a very simple example from the bilinear map. Given the X, it's very easy to compute the GX in a group when we say that the G is a cyclic group. We say have the order very large, like say 2 to the 100, and the group key exchange protocol is running like that. Every party computes G to the, say A, or G to the C, G to the B, and transmits the G to the A to each other. After that, each party computes the session K like this, because in the Alice part, she have A, and she received G to the B and G to the C, and she also computed G, the E, the map E of the G and G to the ABC. This is a property of the bilinear map. The exponent also can be moved to the outside. As the Charlie's part, he have C, but he don't have A and B, but he received G to the B and G to the A. He also computes the final K. Now Bob's place also computes this one. But this is insecure in the presence of quantum computer by the Shor's algorithm. So if there is a quantum computer, so this simple example, or this secure proposal, secure scheme in the classic world, we say many applications will use this protocol, but it's insecure in the quantum world. And it's insecure when the adversary have the quantum computer. So we need a quantum resistant public key group key exchange scheme. There's 2-party key exchanges. The first scheme is proposed by Dean 12, but his scheme is lack of security proof. A secure authenticated key exchange is given by Parhat based on the ring LW problem. And then efficient protocols are proposed like BCNS 15, ADPS 16, and Jinzhou 17. There's also have a group key exchange schemes. The first group key exchange scheme is given by ADGK20 last year from LWE, but their scheme is based on the random oracle. Random oracle is a heuristic assumption. This is a very ideal model and don't exist in the real world. So In this paper, we want remove this random monocle. We just propose a group K exchange from ring LW, a ring version of ring LW, and in the standard model. Another fact is that GKR S20, they show that any ring LW based K exchange need a K reconciliation mechanism. That means a K reconciliation mechanism is necessary for a group K exchange based on ring LW. So this paper, we define and instantiate the multi-party K reconciliation mechanism, for a multi-party K reconciliation. Of course, it's a two-party K reconciliation. So in the two-party case, or instantiation improves the previous two-party K reconciliation of Ding 12. And we define the weak K group exchange scheme and instantiate it. And finally, we use about two primitives, multi-party K reconciliation and weak group K exchange. And we finally construct a group K exchange. A multi-party K reconciliation is like this. It consists of two algorithms, hint and kgen. The hint algorithm on input bi, in the party pi. Every party pi, we say added in the other side. The bi's are predetermined and approximately the same. That means which are very close to each other. And then the pi runs the hint algorithm and outputs hi and broadcasts this hint. This hint is for other parties. It will say that I have 1K and this is hint for you. For your BJ, you can compute another KJ. At the other party PI, he have a BI and the HI's hint, all the hints from other parties. He finally computes the KI. And for correctness, we want the KI's are equal. For security, we want the KI's are random, indistinguishable from a random element from the K space. That means that for every adversary or a bad guy, A, he is given by HI. HI is a hint message, and which is broadcasted through the public channel. So will be seen everyone, and HI is given to A. And we also give this bad guy a K star. This K star is maybe a random element from the K space, or secret K space, or which is properly generated by the Kgen. And the bad guy's goal is to guess this K star is from which distribution. It's from a randomly chosen from the K space, or which is properly generated. Of course, the bad guy have 50%, at least 50% to win the game, because B is randomly chosen by the Boolean number. So this is the security definition. And we instantiate this. Our instantiation is like this, and given the K prime, which is a number in Z, and the hint function outputs an H, the hint message H, and it will broadcast it. And in the Kgen algorithm, given the H and the K, you will compute the K and from in the ZG, the mode G, an integer. The security will show that even if the H is broadcasted, known to everybody, the K is also uniformly distributed, or G. That means even given the H, and the K is random. So, which means that, in other words, which means that H leaks no information about K. So the hint message for others leaks no information about one's secret K. So we prove this in our article. So we have a secure multi-party K reconciliation. And then, but we note that the multi-party K reconciliation need two constraints. the first one is the BIs, the input BIs are approximately the same, and which is previously known to each other. So how we can get these BIs? Obviously, the GKE protocol, the group K exchange protocol can do this, but which is tedious because we want to construct the GKE, so we can't use GKE here. So we just recurse the GKE, and we define the definition and his an instantiation. The security and correctness are relaxed. For correctness, instead of requiring the KIs are equal, we just require them very close to each other. For security, instead of giving one K, here we give all the Ks to the adversary, and want the adversary to distinguish the K, which distributions the Ks are from the uniformly sampled from the K space or just properly generated. Here is our construction. Weak GKE is consists of 3 algorithms: setup, interact, and kgen. In the setup algorithm, on input the security parameter lambda, the participants and the number of participants n. This algorithm outputs a ring element A from the ring, the RQ, which was defined previously, and the PRF. PRF is pseudo-random function, because we don't have a random function in the real world. So we just need a pseudo-random function. And the obfuscated circuit C, which is given in this construction. And this C, PRF, and A are public parameters. And this public parameter is given to the PI. On the PI part, every participant will select 2 ring elements, Si and Ei, from the R, the ring R, by predetermining the distribution chi, and compute Bi as A times Si plus Ei, then broadcast Bi. This is a ring LWE sample type. And finally, the kgen procedure like this. Every party PI given the public parameter and the BI is broadcasted from others. So PI will have all the BIs and Si and Ei, which is the secret key of PI. And the PI evaluates the circuit C, obfuscated circuit C, and session K is output of the C. The C is like this. Input A, BI, Si, Ei for all the interpoles, and the PRF. For every I from 0 to n, it must be bigger. If Bi equals to A times Si plus Ei, the output is PRF value of Bi to Bn. That means if Bi, here's the Bi, equals to this one, if you have a secret K, Si and Bi, and which can correctly compute Bi. So every party PI who have Si and Ei. So every party have one of the Si and Ei will satisfy this equation, and every party can correctly compute the PRF value of this, because every party have Bi to Bn, which was broadcasted by others. So every party has this one. This is correctness. For the security, the outsider who knows the broadcasters BI and who don't have the SIEI. So if one don't have SIEI, this equation will be vanished, don't satisfied. So the outsider will not correctly compute the PRF or anything about PRF. And the BI leaks no information about SI or EI, because our ring LWE assumption says that BI is indistinguishable from the uniform distribution over the R. So here we construct a weak GKE. Finally, we combine our K translation and weak version of GKE. We finally construct our GKE here, group K exchange scheme like this. On the setup algorithm, on inputs a security parameter lambda and participants n. This algorithm outputs a public parameters, which is running by computed by running the setup algorithm of the weak GKE. On the interact part, every party PI will run the interaction algorithm of weak GKE and the K-gen algorithm of weak GKE and hint algorithm from the K reconciliation mechanism and transmit the transmission of I and HI through the public channel. They broadcast the transition I and HI. After that, each party receiving the HIs, all the hint functions and the transitions and his own state STI. Every party will run the algorithm K-gen of weak GKE and compute the KI, which KI are approximately the same. Then use the K-gen algorithm of reconciliation mechanism and compute the final K. So after all, we have two theorems here. If the weak GKE and K reconciliation mechanism are correct with respect to the lambda, and our proposed group K exchange scheme is correct. For security, if the underlying K reconciliation mechanism and the weak GKE is passively secure, so then our group K exchange is passively secure. Here's the further work. The first is construct a weak GKE from lattice problems straightly, or the ring LW problem, which means that our construction of weak GKE is using the very powerful tool of IO, which is very powerful tool. So the constructing a VKE from a lattice problem straightly, which is very meaningful topic. And the second one is constructing multilinear map. As we show in the backgrounds, the multilinear maps will straightly imply a group K exchange, but we don't know any multilinear maps on lattices or ring LW problems. So these two problems, this is the further work or further research topic. And thank you.